Welcome everybody to our presentation on neural network watermarking inside MPAI. And our presentation today, we shall be three speakers, and we shall show you the context of neural network watermarking, the novelty brought forth by the new version of the reference software MPAI just published for neural network watermarking. And this novelty mainly relates to the ability of seamless integration in large comprehensive workflows, as well as on the possibility of embedding these functionalities and thus ensuring distributed neural network workflows. So let's go with the neural network watermarking context. First, about neural networks, of course, this slide may be look somehow rhetorical. We know that today neural networks are deploying an increasing variety of domains. I refer myself to tell practically in all the domains, but at least in our field, this is the case. They are continuously renewed, and not only renewed as architecture or as models or as learning strategies, but also continuously renewed in the way they are used, in the interfaces they are specified towards them, and making them more and more seamless to be integrated in application. Of course, we are still far away from neural network being just as any other software resource, but the way towards this goal, it's already paved, and the huge progress has already been made. Now, if we go a little bit deeper in this analysis, we see that neural networks also act at the heart of critical domains. There are neural networks today ensuring medical decision, so not only helping the professional in their decision, but also acting as a first preliminary decision way. There are more and more application in which life can be at stake, depending on a decision made by a neural network. For instance, autonomous vehicles with passengers, unmanned vehicles in complex industrial plants, and so on. What's behind this evolution? What's behind this revolution? At least two key aspects are important for our presentation today. First of all, machine learning, it's a costly field. While these aspects are not that often discussed, and there are not so many scientific and fancy studies about it, we find a lot of statistics telling that buying professional AI solution ranges from 6,000 USD towards 300,000 USD, or renting a professional pre-built module might cost around 40K USD a year. This is one point. And another point is that the distribution and the usage of the AI, it's very complex. And multiple user can share as a cascade way a same neural network, or multiple neural networks may provide alternative services to end users. So we need to keep a track about what neural network produced, what inference that was provided to which user. On the other side, neural networks can be attacked, can be maliciously altered or modified during their usage. And identifying such modification can avoid faulty functioning and can be of utmost importance. So we speak about neural network watermarking just because neural networks are expected to be authenticated in more and more applications. And the usage of neural networks, the licit usage of neural networks should be tracked. So, what is neural network watermarking? It's neural watermarking in itself. It's a concept inherited from the multimedia content protection. It applies with some modification to neural networks. So watermarking provides tools allowing to imperceptibly and persistently insert some data into an original content. So this procedure, this insertion of additional metadata, it's controlled by a private keys that should be considered like kind of secret information, like kind of cryptographic application. And once inserted in the model, this data should stay there and should be recovered, assuming the private key is available at the detection. So this process generally obeys to three constraints, or to three functionalities. The robustness, it's the possibility of modifying the watermark model, still recovering the watermark. Imperceptibility is the possibility of modifying the content without altering the overall model performances. And the data payload is the quantity of information of data you can insert into a model under the imperceptibility and the robustness constraint. There are not some gold truths, there are not some graal for these properties. According to the application field, according to the facts that we want to ensure authenticity or tracking, there is always a trade-off to be reached about these properties. Neural network watermarking, although these concepts are inherited from multimedia domain, stays a challenging topic. Why? Because generally the mark insertion into a neural network is no longer static, and becomes dynamic. The watermark is inserted generally during the training, and that means that the model in itself, the data to be protected, evolves during the watermarking process, thus bringing in questioning what exactly the watermark refers to. The second difficulty relates to the fact that some large class of neural network watermarking, although inserts the mark in the model parameters, they detect it starting from the inference produced from that model. And evaluating the performance of the model with or without watermarking, so the imperceptibility property, becomes more difficult for neural network watermarking than it used to be for multimedia. And the one who work in multimedia watermarking know how painful this imperceptibility evaluation is. So what is the scope of the MPAI neural network watermarking standard? With this standard, we provide methodologies to evaluate the main aspects of a neural network watermarking technology. First of all, the impact on the performance of a watermark neural network or on its performance. So the first thing we provide are tools for evaluating the imperceptibility property. The second thing we provide is how well a neural network watermarking detector decoder can perform when the watermark model has been modified. So we provide tool for assessing the robustness property. And finally, we provide tools for for evaluating the computational cost of injecting, detecting, or decoding a data payload in the watermark neural network. Keep in mind, MPAI do not provide standards for achieving the watermarking in itself. We let this open for any application designer. What we provide are tools for assessing how good these technologies are. And our technical specification came across with a reference software that it's already to its second release. The purpose of this reference software was initially to provide an instance of MPAI neural network software for the image classification task, but with this second version and with the demo you will see in a couple of minutes, you will see that we move forward towards other tasks like generative neural networks. And to upgrade conventional AI-based processing workflow with traceability and integrity checking function. So with this second version, neural network watermarking, it's no longer separate component. It's no longer a standalone software you can deploy a turn. It's are dynamic components that can be seamlessly integrated with the MPAI workflows and even beyond the MPAI with any neural network workflow. Any, of course, as always, should be specified. So the software has two key components, the injector and the detector. Actually, these two tools allows us to evaluate the property. So these are generic tools. Our software implementation, this injector and decoder, actually provides hooks towards external modules that are the neural network watermarking software that can be integrated. The only request we have for them is to have these two functions separate at two functional modules, and they can be taken aboard in MPAI. We already made an initial presentation of the first versions that are made available by MPAI, and through these slides, by clicking, you can go there. So I shall give now the floor to Carl to explain the main novelty of the version 1.1 and to make you a live demo about this.
So just to show you, this is a use case we will discuss. So first of all, hello everyone, and this is a use case we will discuss today. So which is AIF that we can call multimodal question answering, because it takes a speech and an image as input, and the answer to the question according to the context, which is the image, is given to the end user vocally. So it's a vocal answer. And in our use case, we want that vocal answer to be watermarked, so the output of the text-to-speech to be watermarked, and that we can detect it if there is a watermark in the audio or not. But first, let's discuss a bit about the controller. So it's a Python implementation of the AIF standard. I won't go that much in the detail, but everything can be found on the GitLab on MPAI, including a README to understand it. But in a nutshell, you have a controller that will receive the input given by the user agent to the controller. So using the input.py, you send something to the controller, and the controller will process accordingly. And when I mean accordingly, it's using APIs that are also defined in the AF standard. But for example, the MPAI-AF get and parse archive take a zip file containing all the needed AAMs and the JSON metadata, which make the link between the different AAMs and the topology of the AAW. And this AI.zip, for now, it's a file that I have in my computer, but we can imagine in the future it can be directly downloaded, from the MPAI store. So let's demonstrate the use case. So as I said, I prepared just a small lab, let's say. So on the left, I will have the controller that will receive the input coming from the right terminal. So for example, the first thing that I need to do is to parse. As I said, I need to obtain a zip file. So for now, it's on my computer, but it could be downloaded from the Empire Store in the future. After some initialization, it will parse it. So now is aware that the output of the audio to speech recognition should be an input of answer to question module, and so on. So the topology and the type of information that is linked from one to another. So I can run it. And it will ask me for the two inputs that the user agent should give. So first, it's the question of audio, so it's an MP3 file, but in the future it can be directly questioned by the end user. And also it will ask for the context, which is in my side a raw image that I can show you. So it's a photo taken in Paris, in France, of the Sacré-Cœur. So let's give it as an input. Sorry, it's this one. Yeah. And then we will let it process. So the text-to-speech has answered our question orally, and we also have a wave file which will be used at the checker side. And we also, just to make sure, the output of the speech recognition module was our question: in which country was this photo taken? So now we have done this side, so the AW of multimodal question answering. And our objective is to check if this audio answer was really produced by the text-to-speech that is watermarked. So for that, I'm using the... Sorry, we'll make some space like this. For that, I just need to drag and drop. So this window works as a checker. So I just drag and drop and I ask for the watermarking proof. And as you can see, it starts processing. It takes some 10 seconds before answering. And yeah, the audio I obtain using the AW is watermarked, and just to be sure, we can test with the audio of the question, which should not be watermarked. And it is not watermarked. So the output of this audio is watermarked, so as expected. So we have watermarked this AW. And if I take any other audio, there is no watermark in it. And that's it. I will wait for the question maybe at the end of the presentation, but that was the current use case. We
Okay.
stop sharing.
Okay, so I shall take the hand for just some concluding part. I hope you see my screen correctly. So what are the conclusion on this neural network reference software? First of all, this current second version, the version 1.1, it's available on the MPAI GitHub. So assuming you are registered and with MPAI, you can access, download, and start using it as presented by Carl. Of course, we also put on the repository a video with instruction and making things easier for you to have the hands-on. What is the main novelty? It allows neural network watermarking to be seamlessly coupled to complex neural network workflow. We demonstrated here how this goes with MPAI. The workflow was quite complex. It was first you have a video file, so it was first an AIF that converted from audio to text. Then it was text to image querying that produce as output a text, and finally it was a voice synthesis algorithm. And all this in all these tasks on all these tasks, sorry, the watermark can go at any level. We illustrated it at the final level, but can go anywhere with simple lines of codes as shown by Carl. What's next for today? Alessandro will show you how the same software can be used in order to bring watermarking in embedded devices and to use that for ensuring distributed workflow established this time outside the MPAI. So I shall stop sharing now and I shall let Alexandro come share the screen.
Okay. Can you see my screen?
Yes, we see it and we hear
Okay,
it.
thank you, Mihai. Hello, everyone. I am Alessandro Carra, and I am a software design engineer for ST Microelectronics, which has joined the MPAI this year as an associate member. Before starting the presentation of the project, I will introduce you to the distributed intelligence and the TinyML context. AI in general and neural network models are often perceived as complex systems that require cloud-based services or powerful servers to operate. And as shown on the left side of the slide, all data collected at the edge by the sensor have to be passed through the gateway to the cloud, where the application and the AI algorithms will run only there. Using such an approach arises the need to have multiple routed connection capable of communicating every single moment to obtain the results. This data flow requires time and energy, even because the costs will rise proportionately to the amount of data and devices added. A different approach based on the distributed intelligence has been developed. The data here acquired and processed by AI within the same device, so in the sensor and the actuator unit. Data, so the data is processed at every level, beginning from the lowest level of the diagram, representing the sets and actuator unit, composed of MCUs, sensors, and other tiny electronic devices. Not all applications can carried out in these less complex devices, but the output data might be sent through successive layers with which adding more sophisticated analytics until reaching the cloud. And in the cloud servers, as the central repository concatenating all. Okay, the intelligence distribution process enables the division of complex problems into simpler tasks, thereby reducing unnecessary latency and bandwidth usage by guaranteeing greater security for the data, as it is not transmitted beyond the devices unless in a significantly processed form. That can be prediction or other analysis from the analytics. Furthermore, this approach offers substantial energy savings and allows for data processing even without connectivity, with reduced inference times. Okay, by adopting this technique, some application and AI algorithms have to be shifted from the cloud, represented on the top of the slide, to the edge. This requires re-engineering them to comply with the constrained resource available in the tiny devices made up of sensors and microcontrollers as represented in this slide. The board present on this slide is the one used in this project and in which the neural network model for image classification has been deployed. The recent advancement in AI, together with the widespread use of edge devices, represent the motivation in using TinyML as a solution where smart services can compute as well as they reason without the need of external interaction to obtain a low total system response time. With the TinyML, the TinyML word are broadly defined the machine learning architecture, techniques, tool, and approaches able to perform in low power devices. And it is also a non-profit organization with the mission to accelerate the growth of a global community of people leading the edge energy efficient machine learning computing. Based on this definition, TinyML context is well established nowadays. However, the challenges have already been set since the above-mentioned shift from cloud to edge isn't so straightforward. So a non-negligible effort and expensive resources are necessary, needed to get accurate results from these NN models. That's why the intellectual property shall be protected by same or a similar way it was done for the complex AI model. Additionally, I'd like to mention that we choose the image classification use case among the 4 referenced by ML Commons in the performance inference tiny benchmark. We preferred to use this NN model from ML Commons because it's kept as a reference within this community, and also because the source code is public and replicable. Okay, until now I introduced the distributed intelligence approach and the TinyML context and the motivation that led us to face the TinyML challenges and to choose the ResNet 8NN model from ML Commons, training it with the CIFAR10. Now I will present you our project about deployability and MPAI robustness evaluation of watermarked and neural network models on MCU. Okay, we used two types of data, the CIFAR10 dataset and the trigger dataset. The trigger dataset is composed of 100 abstract images uncorrelated to each other, represented here. A state-of-the-art black box watermarking method has been used to generate and assign in-current label, represented here. Further on, the watermark has been embedded using the mentioned method. Then a watermark and then model has been obtained. Also, attacks have been simulated on the model to investigate the watermark's strength following the MPAI-NNW robustness evaluation procedure. The STA-AI Edge Unified Core Technology is a common ST tool that automatically converts the pre-trained NN model to C code compatible with MCUs that will use optimized inference runtime. This is necessary to run the inference and evaluate the robustness of the watermark. Okay. The results I will be showing you have been achieved with this tool and its hybrid that runs on STM32 microcontroller. Okay, before I introduce the TinyML challenges, and now a point from this is being shown. The inference are not run on a powerful device anymore. Therefore, passing from to an MCU, its constrained resources need to be considered. In terms of the order of magnitude, the available memory size shift from terabyte or gigabyte to memory or kilobyte size, and the frequency, the clock frequencies decrease to megahertz. Particularly the low power STM32H7 microcontroller, the one used to run this inference in this project, within this project, has only 1 megabyte of RAM and 2 megabytes of ROM, and 480 megahertz clock frequencies has been chosen. The STA-AI analysis on the pre-trained model with the CIFAR10 and the watermark one shows that the same number of parameters and the same amount of required memory has been as is needed. Hence, no extra resources are needed to deploy the watermarked neural network on the MCU with respect to the unwatermarked one. Okay, here you can see the accuracy score of the performed inference. It's been done by combining the input data, the AI framework, devices, and neural network models presented till now. The accuracy score represents the number of correctly recognized images divided by the total number of images given as input to the tested model. Okay, in this column, you can see the different AI framework, Onyx and PyTorch, that runs on a laptop or any type of PC or server, and STAGI that has been used with the MCU. We evaluate the image classification accuracy with the CIFAR-10 to be sure that the overall accuracy remain the same until the Gaussian, the attacks perform not so well. Okay. And in the trigger dataset column, we evaluate the robustness of the watermark embedded in the different models using the trigger set. In the cell highlighted in green, are shown the models with the watermark detected correctly, considering that only 10% of images could be predicted wrongly. The tests have been done for unwatermarked, for the watermarked, and for the attacked models. Following MPAI-NNW procedure, Gaussian noise has been added to the weights. A certain percentage of weights have been pruned, and also the weights have been quantized in using various bit depth. Based on numerous test results, we have demonstrated that the tiny neural network model remain robust when the watermarking method is applied, up to the point where the original accuracy begins to drop, as we can see in the quantization attack from 5 to 2 bit. This is valid for the inference run on the MCU and in Onyx and PyTorch framework using the laptop. The difficulty of hiding a robust watermark in just a few parameters should not to be underestimated as in this case. Okay, now I will show you what we use to do this project. We collect all the explanation and description of what we did in the project and the source code inside one document, one Python notebook that allow the future user to understand and both run within the same documents. Okay. Okay. Now I scroll down this notebook. This is the notebook we developed. as I introduce you here, there is a section, images, text, and the definition inside this cell of the different part of the process. Okay, and now I want to show you a brief demo that include a inference, live inference that runs on STM MCU. Okay, I will run. Okay, and as you can see, I am running this command using the STAGI tool, XUBI version 8.1, using and specifying only one file, okay, this 001 picture from the trigger set, and and also the expected class, since it is a image classification task. Okay, the validation is done. Here there are all the lines that are the output from the validation, and here I can show you that this is a confusion matrix which represents the predicted class and the class from the ground truth, from the label. Okay, and this represents the image predicted as class 6, the same of the original ground truth label. Okay, and so the accuracy is 100%, and the watermark can be recognized if we use 100 or more images to test it. For time reason, I show you only one image. Okay. Okay, concluding, what we did is to successfully watermark a tiny NN model with few parameters. And what we demonstrate? We demonstrate that the watermark NN deployment on the MCU doesn't need extra resources with respect to the unwatermarked neural network, speaking about the number of the parameters and the RAM and ROM size. And the ownership of this watermarked model can be proved. The watermark was detected, as I shown you, in the model with and without MPI attack simulation. And how you can replicate this? You can replicate using this all-in-one Python notebook. And that's all from me.
Thank you, Alessandro. I think it's now time to conclude this presentation. So, as we went through these three topics, let's see our next steps. Of course, the first one will be to make NNW available on MPAI store as a service. So this task goes along with the MPAI efforts for specifying and launching this store. So what means that? It's the technical means for creating the resources for dynamic allocation of the neural network resources, and the creation of the template for each of the MPAI-NNW use cases. So these templates rather depends on what you want to do with the watermarking and not what it's the task the neural network is performing. A parallel direction relates to exploring the applicative perimeter of distributed and embedded NNW. As you saw in the Alessandro presentation, we dealt there with the image classification task, but as he clearly stated, TinyML have various other tasks, and it will be nice to see what among these cases can be enhanced with neural network watermarking facilities. So I thank you for your attendance, and let's open the discussions now.